Welcome to the Learning with Unstructured Data course. I'm going to split these 2-hour sessions into 2 lectures with a short break between them, and then we move on to the questions and answers session in the Zoom link I provide in Clip. So in this first lecture, this first block before the break, I'm going to give you an overview of the course, how the course is going to work, what are the objectives, and then give you some motivation for using deep artificial neural networks for working with unstructured data. So I'm going to talk a bit about history of artificial neural networks and AI in general, how this fits with machine learning, and focus on one important aspect, which is this power of nonlinear transformations. So those of you who had machine learning last semester already have an idea of this, but we're going to review this, and I'm going to tell you what deep learning can offer, especially when you are dealing with unstructured data, but more generally for solving machine learning problems. Then after the break, I'm going to try to explain a bit better how deep learning can fulfill these promises that I'm going to end this first block with. So let's start with the more formal aspects of how this course is going to work. The basic objectives are to give you the foundations, the knowledge of how deep neural networks work, and also a practical experience in applying these models to processing unstructured data. So we're going to focus on the kind of networks that can help us deal with unstructured data, such as convolution networks, recurrent and generative models, and so on. We're also going to talk about autoencoders for manifold learning and feature extractions, about knowledge transfer, where we can use models that were trained with some data set and use that knowledge the model acquired to improve performance or to make it easy to learn some different tasks. So we're going to focus on those kinds of problems and solutions. And this will also have a very practical component. So you're going to learn to work with the TensorFlow and the Keras API. We're going to work in Python, and we're going to be using the same framework that we have been using in machine learning. So those of you who took machine learning last semester will just continue using the same basic tools that we use, only with the addition of TensorFlow and Keras specifically for deep learning. So we're going to split the semester into 2 parts. This course is a collaboration between the computer science department and the mathematics department. I will be giving the first part, where we will cover the more theoretical foundations, the concepts, and the basic techniques that you'll need. So I'm going to give you an introduction, the unstructured data and deep learning, and how deep learning help us work with unstructured data, and also how to work with artificial neural networks using this framework, TensorFlow and Keras. We're going to cover basic neural networks, convolution networks, autoencoders, and knowledge transfer, and you should reach the midpoint of the semester with not only these theoretical concepts well understood, but also with the basic practical knowledge of how to get these things to work using TensorFlow and Keras. So the assessment by the middle of the semester will consist of one test. This is a theoretical assessment that is going to account for 30% of your grade. This will be on the tutorial session on April 22nd. It will be an online test, so similar to what we did in machine learning last semester. You will also have to submit a tutorial, an individual tutorial on TensorFlow by April 28th. So this will be focused on demonstrating that you can use TensorFlow and Keras for implementing these networks and for solving these problems. So you can choose the topic that you want. The idea is to make it a demonstration of what you know how to do with TensorFlow and Keras. And this should get you ready for the second part of the semester, starting from April 29, which will be with Professor Rui Rodrigues from the Mathematics Department. And this second half is going to be more focused on practical applications. So you'll be solving real problems using these techniques. And during the second part of the semester, you will be working on the final project that can be split into several deliverables, but it will be a final project, and this will account for half of your grade, which you must submit by the end of the semester. So Professor Rui Rodrigues will give you more details about this later on, but in principle, since there are not many students enrolled in the course this year, we will do this assignment, this final project, individually too. So I think all these grading materials, these projects that you have to do, will be individual. So this is the basic resources for the course. You'll have lecture notes, the slides, and links to the recordings of the lectures on the course page. Also, we recommend that you follow this subject matter by reading up on the Deep Learning book by Goodfellow and others. You have also this paper on Nature Research in 2015 on deep learning, which is an interesting read to give you an overview of this subject. And also these deep learning methods and applications, you can see several of the algorithms and the subject matter there. So in general, I will give you some recommendations about both books where you can read up on the subject matter of each lecture. And the idea is that sometimes it's best to see things explained in different ways, because different people have different ways of thinking about things. And so maybe one book is better for some of you, the other for others. So you can look it up and see what works best in your case. For the actual work, so the tutorials, in the classes, the assignments, and so on, we're going to use Python 3 and TensorFlow 2. The easiest way of using this in your own computer would be to use Anaconda, exactly like we used in machine learning last semester. You can install this distribution, and then you can install TensorFlow locally. If you want, alternatively, you can also use Google Colab. So you have a Gmail account with the university, so you can use the Google Collaboratory online, and there it's easy to use TensorFlow too, and so you don't need to install it on your own computer. But I would recommend installing it locally because it may be more convenient. You don't need to be connected on the internet. You don't have limitations on how long things are working, and so keeping the connection alive and so on. So it may be more convenient to use your own computer. Okay, so let's look at an historical overview of how we got here to deep learning. We can sort of pinpoint the beginning of artificial intelligence research to this workshop, this summer research project on artificial intelligence in 1956, where several of the top experts in computation and similar fields at that time gathered together to try to settle on how to make machines intelligent. So the idea was that these aspects of learning, reasoning, and so on, we could in principle specify them so precisely that machines could automate it and simulate it adequately. So the initial idea was that if a few intelligent and expert people gathered together for a few weeks in summer, they would get this more or less solved, and then it will be a matter of implementation. Of course, this was a bit too optimistic, but it produced the first step on artificial intelligence research, which at that time started to become very dominated by rule-based systems. So basically, humans could provide the rules, and the computer would automate working with the rules, inferences to reach conclusions. So sometimes you could use also these systems to derive new rules, to infer new rules from data and so on, but it was very much based on specifying rules and then reasoning with those rules. One example of this was this Mycene program in 1975 that had rules provided by humans to try to identify different types of microorganisms based on the evidence of test results and so on. So you could have rules like the stain is gram-positive and the morphology is a coccus and growth is in chain. So if these three are true, then it will reason that this is a streptococcus. So it would conclude that it was a streptococcus. This is an example of these first rule-based expert systems that use the computer just to work with the rules and infer the results given the rules and the data. But also at this time, even earlier, some scientists started to consider theoretical properties of the neurons that could be used computationally for simulating some kind of brain, some neural system. So by 1943, there was already this model of the neurons by McCulloch and Pitts, which mimicked how biological neurons work. So the neuron cell has these dendrites that receive the input, so to speak. They are sensitive to stimulus. But if the stimulus is too small, the neuron doesn't do anything. If some threshold is passed, then the neuron will fire an impulse along the axon, and then it will reach these synaptic terminals and pass on this impulse, for example, to another neuron, to a muscle cell, or something like that. So this kind of nonlinear response, where we have some combination of the inputs of the stimuli, but then a nonlinear response for the output, was modeled using this kind of function. So we have an input vector that is a series of numbers, and then we have also a vector of weights that are going to mimic the sensitivity of the different dendrites. So if you have a large weight, then even a small input will make it very significant on the overall function. With a smaller weight, it will be less sensitive to that input. And then we sum the products of all these weights and the inputs, and we have this net input for our neuron, and then we pass this through a nonlinear activation function that will mimic this nonlinear response of the neuron, which is if the input is too small, the neuron doesn't do anything. If the input passes this threshold, it will fire the output. So one example of this nonlinear function could be just a threshold function that determines if the output is 1 over this threshold or 0 if below this threshold. And this was actually implemented in 1958 by Rosenblatt as the perceptron by adding to this model a rule for learning the values of the weights. So what each of these value would be learned by the system depending on the data and the problem we are trying to solve. And this was something that was really seemed very promising. And we have here an excerpt from a New York Times news about this, which this electronic computer was expected to eventually learn to walk, talk, write, reproduce itself, be conscious, and so on. So they thought they had solved all of these problems with the perceptron. And the idea was fairly simple. We have this, this is the perceptron is just one neuron using this rule. So we take the input, multiply by all the weights, and add an additional bias. So this is, we can just imagine this as if we had a new input here that is always 1. So we have an additional weight that counts always as multiplied by 1. So we can use that to adjust where the threshold will fire. It's a free parameter that we have here. So we just multiply all the inputs by the weights, add this additional free parameter, and if this is greater than 0, the output is 1, otherwise the output is 0. And now the trick to learn to update these weights is to check if there is a difference between the output of the perceptron and the target value that we want. So if for a particular example we would like the result to be 1 and the result is 0, then there is a difference here. And so now we are going to adjust all these weights by a small fraction of that difference multiplied by the value of the input that is going through the weight. So if there is a larger input, we are going to give a bigger update to the weight. If the input is small, we'll give it a smaller nudge to that weight. But we're basically going to adjust the weights for all those examples that the output misses. So every time we have an error in the output, we adjust the weights a bit, and we keep doing this with lots of examples until the perceptron starts getting everything right. So this would be the idea, and this was actually first implemented on this IBM 704, in software. And it learned to distinguish between these punched cards if they were punched on the left or on the right side of the card. So given 50 examples, the perceptron learned to tell the difference between the cards. But then was actually implemented as a machine. It had a rudimentary camera with 400 pixels, so 20 by 20, that could recognize brightness and input different images, and then there were these electric motors that adjusted the potentiometers that would give different weights to the input. So it was actually a machine that could learn by giving it examples of what was one class or the other, and it would automatically adjust all these weights using these potentiometers until it got the classification right. So at first, there was a lot of hype because this was a machine that could learn to solve problems, and they thought it would be able to do everything. But the problem is that when we take a linear combination of the inputs and then do something, a classification based on that, we can only separate our classes with a straight hyperplane. So depending on the number of dimensions, but it would be a linear classifier. So the perceptron is just a linear model, and if we have something that cannot be split apart with a straight line, then this will not work perfectly. It will find, if we keep adjusting the weights, it will find the best weights for trying to split between the two classes, but it will fail at some points because it's impossible to divide them with a straight line, and one single neuron cannot do more than a straight line. So this was a big disappointment because it turns out that the perceptron had exactly the same power of classification as something like logistic regression or generalized linear models that was already known at that time. So basically, we can even see the similarity. Logistic regression is this model that tries to separate between different classes by estimating the probability of some example x being in class 1. So let's say we have this function that we're going to learn that has some parameters that we can adjust, and is also a function of the input, the example we presented, and it will try to approximate the probability of something with those particular values, those particular features belonging to class 1. And basically we want to put a division line between the two classes, so at the point where the probability of belonging to class 0 is the same as the probability of belonging to class 1. So one is 1 minus the other, they are both 50%. We can solve this using this function, the sigmoid function that has this S curve, and this will turn up the maximum likelihood solution. Will give us this minimization problem of the logistic loss. So basically, this was something that was already known. We can use this to compute all these weights that give us the best line dividing two classes, but it's just a linear classifier. It gives us a straight line. And if we do this with the neuron, we can do the same thing, because if we use as an activation function, instead of this one that Rosenblatt proposed, that was just a threshold, 0 or 1, if we replace this activation function with the sigmoid function, this one here, then mathematically this is exactly the same as logistic regression, because all of these weights are there, are all these w's. There is the additional one, the bias, is this w0, and then we have this activation function, so we can use one neuron to do exactly the same thing as a logistic regression. Okay, so this is a problem because this is just a generalized linear model, so something that can do linear classification, and this was already known way before the perceptron. So this was very disappointing, because it turned out that all these promises that they thought these systems could do turned out to be fake. They could not solve those problems in general. So this also resulted, this along with the failure of all those expected results for logical processes, for reasoning, automated reasoning, and so on. We have this between 60s and 80s, this artificial intelligence winter, where people were mostly disappointed by this. So during this period, logic systems were dominant in artificial intelligence, things like Prolog, for example, but artificial intelligence itself was not very popular because it was very limited what it could do. However, in the 70s, this algorithm of backpropagation already appeared in different contexts, in engineering and so forth, and it was adapted in 1986 to train multi-layer artificial neural networks. And this was an important step, because if we have multiple layers, we'll see we can go beyond these limitations of a linear classifier. So let's move now to the part of artificial intelligence that is machine learning. Once again, we have something that is not new. The basic idea, we have this from 1959, is that we can give computers the ability to learn. We don't need to tell them exactly what to do. We can give examples, and they will learn how to solve the problems that we have. This was formalized more carefully by Mitchell in 1997. So basically, we have some program that can learn if it can improve some performance at some task. So we have a measure of the performance, we have a specific task, and if the program can improve from experience, where experience is a set of examples, something that we can show the problem being solved, then we can say that the program is learning. So we can actually formalize and specify all of these aspects of machine learning, and so define what machine learning is. For this, basically, we need the task that we must perform, a measure of performance, because we need to improve that measure as the system learns, and we need the data used, so the experience the system will get is in the data that we're going to supply. And there are lots of examples of machine learning that are used today for filtering spam messages, classifying images, doing diagnostics, like with diseases and things like that, speech recognition, and so on. So there are many cases where we do not know explicitly how to solve the problem, but we can provide a machine learner with lots of examples and let it learn how to solve the problem. And this is the basic idea of machine learning. So we can consider different kinds of problems in machine learning, just to look at 4 basic kinds. One we call unsupervised learning, consists basically on having the system learn new ways of representing our data. So we want to put in all the data that we have, so the examples, and each example has a set of features, set of values associated with it that characterize it. We feed it to the learner, all of these examples, and the learner will give us new values associated to the examples. For example, this can be cluster labels where we put together things that are similar. It can be a different representation of the features by compressing them into lower dimensions, something like that. So in this case, we call this unsupervised because we don't need some additional label that we can use to check if the learner is going in the right direction or not. So we just let it learn by itself. Supervised learning is different in that sense that we have some target values that we are not showing the learner, but we want the learner to try to predict these target values. This can be, for example, classes for our images. We have images of cats, dogs, horses, and so on. We know which class each image belongs to, but we want the system, the learner, to be able to predict, to tell us which class each image belongs to. So what we're going to do is we're going to check for our training set where we have these labels, to check if the learner is getting it right or wrong, and we give some feedback to the learner to adjust the parameters as we are improving performance in this task. So, for example, Rosenblatt's Perceptron did this in order to fit the best set of values for the weights. We can consider semi-supervised learning where we mix the two together. We have some labeled data, but we have usually a lot more unlabeled data because labels may be expensive to get. We need people to actually look at the examples and label them. So we can join the two together. We have other kinds of problems where we cannot immediately and directly use feedback to adjust our parameters. In reinforcement learning, for example, we are teaching, for example, our learner to play some game. For each move, there will be some consequences, but it's hard to tell if the move was good or not until we reach the end of the game. So if we lose the game, then probably there were some bad moves there. If we win the game, then those were good moves that led us to victory. So we have some output and some way of evaluating the result, but this is not immediate. We cannot simply use each action of the learner, each choice of the learner to feedback into the parameters and adjust the parameters. So these are some different examples of machine learning problems, but they all have this idea in common in that we do not have an explicit recipe for solving the problem, but we have examples that we can give the system and hope the system learns some pattern there, some way of solving what we want solved. So these kinds of problems that we can solve with machine learning, like extracting new features, approximating some target value, optimizing policy, and so on, the traditional approach is to use very different models for this. So the different techniques for solving these problems are very different among themselves. A clustering algorithm, logistic regression, things like that, they have very different architectures, very different principles, very different approaches. And this is the general way that things have been done classically in machine learning. Machine learning also improved a lot in the recent decades as some initial problems were overcome. So basically, the beginning of machine learning, we can see it as far back as the 1800s, where linear regression was used, for example, for predicting planetary motion. So least squares linear regression is an example of machine learning where we have a model, and then we have examples that we are using to adjust the parameters. Of course, by 1800s, they did not have computers to do this automatically, but they could do this by hand, compute the parameters, and so this was the first example of this kind of modeling, where we use examples to fit the parameters of our model. Then, more recently, in the 20th century, we have things like logistic regression, probit regression, and so on. And these techniques basically consist of having a set of features that humans extract from the data. We think about what can be useful for our purpose, and so we go measure those values. These are the features of our examples. And then we have a linear classifier that can separate different classes using some linear discriminant, or we have something like regression and so on. I'm focusing mostly on classification, but we can think of this more generally. But the idea is that we have a set of features that we chose, and then we have this linear model that will give us a way of predicting some target values as a linear function of the features. But this, as we saw, is very limited, because if we only have a linear model, there are lots of problems that we cannot solve adequately because they do not give us, say, a linear separation between the classes or a straight line in a regression or something like that. Things got a lot more interesting, and this we may see this as the beginning of this era of machine learning in the 90s, when AI started shifting from this knowledge-driven approach where we have these rules, we specify the rules, we do these inferences and so on, and it started working more with data, with lots of data, and with more powerful algorithms. For example, in 1992, the kernel trick for support vector machine allows us to do something different here, which is easily do a nonlinear transformation of the features we chose, and then do linear classification. These kinds of nonlinear classifiers, such as random forests, support vector machines, and so on, really started to have lots of success in solving problems that could not be solved with linear classification. And also by this time, neural networks started having some success too. So basically, when we start having more data and we start having a way of doing these nonlinear transformations, then machine learning can become very powerful. And the reason for this is what happens when we use this nonlinear transformation. So let's suppose we have this data set, we have these blue dots here, red dots here. Actually, these are gene activities in the 2 dimensions, and these are tumor and normal cells, but this could be any kind of problem. And if we can draw a straight line and separate our classes, then these classes are linearly separable. But if we only have a linear classifier, we can only solve these kind of problems. If the classes are not linearly separable, then we cannot solve these problems. And this would be an example of using logistic regression, of using one single neuron with this kind of activation function. So this is that sigmoid function we talked about previously. And if we do this, for example, with logistic regression, we basically have the features that we chose, those gene activities, for example, and then we do this linear classification. We find the best line that separates the 2 classes, and this line corresponds to the midpoint here on this curve that predicts the probability of belonging to class 1. So from here forward, it's more probable that the point belongs to class 1. From here to the back, it's more likely to belong to class 0. So this is the general idea. We find the parameters for a linear classifier. We get something like this. This would be the output function of our logistic regression depending on the features of the examples. So this would be class 0. They have a low probability of being in class 1. And this would be class 1 here. Since we are working with a linear combination of the features, this will always be a straight line where we are separating the 2 classes. Now, if we have something that is not linearly separable, for example, we have this blue dot here and some red dots there, we will find a line, but it will not be a perfect solution because it does not allow us to correctly classify all the points in our data set. What we can do in this case is to keep using a linear model, but instead of doing this just in 2 dimensions, we're going to add an additional dimension, an additional feature that is the product of the other 2, for example. So this is a nonlinear transformation. This feature is not a linear combination of the others. It's a nonlinear transformation. And now we have everything in 3 dimensions, but the distribution of the points is on a curved surface. So if now we use the same model, a linear model in 3 dimensions, and we get this plane here cutting the 2 classes, actually when we project back to the original space, this will be curved because we are projecting back through this nonlinear transformation that we made to the data. So this is really what nonlinear transformations allow us to do. We move our data into a different representation. It may be with more dimensions or not, but it's a different representation where everything was twisted enough so that a linear classification in that different space now corresponds to something that is not linear in the original space. And we can do this how much we want. For example, we add the product, the square of the first and the square of the second feature, and now we can get something that is even more curved, and so on. So this is the power of doing nonlinear transformation of our attributes, which allow us to work with the linear classifier in a different representation space and solve problems that cannot be solved by a linear classifier in the original space. Now, with logistic regression, this is not very practical because we have to do everything by hand, but support vector machines do this automatically. The reason is that, well, without going into details, how we can compute the parameters for a support vector machine is to solve this constraint optimization problem where we are finding the Lagrange multipliers for the examples, and this basically depends on the inner product of the examples. So by using a kernel function, we can compute these inner products as if they would come out in a much higher dimensional space after some arbitrary transformation, but we can do that without heavy computational costs. So support vector machines can do this nonlinear transformation very efficiently, and basically we choose our features, the support vector machine does the nonlinear transformation, does the linear classification after the transformation, so in this other universe where our data was all twisted and reshaped, and this can help us solve complex problems of classification. For example, we have these data by adjusting regularization parameters, the kind of kernel and so on. We can obtain a discriminant like this that follows smoothly the frontier between the red points and the blue points here. So even though the actual classifier is linear, it is working on a different representation of the data that was obtained by using these kernel functions on our examples. So this led to a lot of success in machine learning because we can use this, we can solve, in theory, any kind of problem like this. But the problem is that these things that do not always work well in practice, as we keep adding new expansions, different models, things like that, we may start to adjust too much to aspects of our training data that do not really generalize. And in fact, there is an important theorem, this no free lunch theorem, that tells us that for any model that we can use, if it's better than average at some task, it will be worse than average on other tasks. So we can imagine this in the sense that all models will have some kind of structure in the data where they can easily adapt and generalize. But if the data is different, then it may actually be misleading the model and it will perform worse than just, say, random choice or something like that. So basically, for all these models, we need to have some implicit assumptions about the structure of the data. And if those assumptions don't hold, then the model performs poorly. If they are true, then the model performs better. So there is no single model that we can say is best for all tasks. And one problem that generally occurs is that as we try to fit the data that we have for adjusting the model, the training data, too well, we start fitting aspects that do not generalize outside the training data, and so the model starts to actually perform poorly outside the data. For example, if we separate these classes with this discriminant, we get some errors here in some points on our training data. If we improve too much the power of the discriminant to separate them, then the model starts making assumptions about regions, for example, over here, that may not be very reasonable. So to assume that this would be a red region and any point that falls here should be red is probably very, very risky, very chancy, because it may not be true. But it works well for the training data. However, the generalization may be much worse. So this is basically a problem that we need to solve by adjusting basically the kind of model that we use, how many parameters we have, the kind of how powerful the transformations that we are doing. And so we generally need to have one set of data for adjusting the parameters of our model. This is the training set. And as we increase the power of our model, we generally get better and better at solving the problem in that specific set of examples. But eventually we start overfitting and we start performing worse and worse outside that set of points. So for this, we need in general to have different data sets. We have the training set that we use to adjust the parameters of the model, and then we have points outside the training set that we can use either to choose other aspects, for example, different models, meta-parameters, regularization, and so on. And this is called the validation set. We are using data outside the training set to decide which is best, which is the best combination of models and hyperparameters to use in our problem. And we also usually use a test set to get an unbiased estimate of the true error. That is the error that our model will commit in general, on average, outside the training set when we are using it for real. It's important to distinguish these two because if we are using some examples to decide, for example, choose the best model, then we are already biasing that estimate by our choice. So we need to have some set that was unbiased by any choice. So this is the idea that we need to do. We need to try to adjust things so that our model performs best on our particular problem without overfitting our training data and losing the ability to generalize. And now we have some things like selecting the model, adjusting training with regularization, using more data if the model can use more data, and we have. So there are lots of things that we can do to try to tackle these problems. So basically what we want in machine learning is, first, we need to be able to do these nonlinear transformations, because without those, it's very hard to solve problems. We need some way of solving problems where it's not a straight line that gives us the best solution. We also need to adjust the models that we have for different problems. There is no single model that works best for all different problems, so we need to look for the best model for each particular problem. We also need to find the right features to feed into the model. So all of these examples, we have been looking at this kind of scheme where we extract some features from our data and then we do a linear classification or a nonlinear transformation and then a linear classification, but someone has to do this part. Someone has to figure out which are the values that are going to be fed into the model. And we also need to be able to have some ways of preventing overfitting. For example, selecting between different models, using adjusting the way the model is trained and so on. And we ideally should be able to use as much data as we have. It's always better to have a model that can take all the data that we have and not be limited by some computational complexity or things like that. So in classic machine learning, and by classic I mean not using deep learning and neural networks, we have many algorithms that do these nonlinear transformations, and so we have many different models. We can choose random forests, support vector machines, different things, different techniques to try to solve these kinds of machine learning problems. And for these, we also need the right features. So we have techniques to select features, to extract features, but we need to be working with the data, applying those different techniques, evaluating the kind of features that we have, and then also choosing the models depending on the features that we have. And so this requires a lot of work, a lot of human intervention at this stage. Also, to prevent overfitting, we can use regularization, model selection, but this will vary a lot between different models, different kinds of approaches. and some models are better at working with large amount of data, others are not. For example, support vector machines, if you have a lot of data, then it becomes really expensive computationally, because it's quadratic with the number of data points that we have. We need to consider all the pairs of examples, and so it can be very difficult to work with large data sets. So what I'm going to try to convince you of during the second lecture, after the break, is that with deep learning we can solve these problems. So we have a stack of nonlinear transformations in a deep neural network that can solve, in general, whatever transformation we need for our data in order for the problem to be solved at the end. We can build many different models with neurons, but they are all basically the same kind of thing. They are all built from connecting together these artificial neurons that we model mathematically in a way similar to what we saw before. We also need eventually to have a good representation of the data so that the problem can be solved. But with deep learning, we generally don't have to do this ourselves. We can let the neural network figure out how to represent, how to transform the data adequately in order to solve the problem. So this is actually part of the training of the model, and not so much something the human must do before using the model. We have many ways of regularizing the training of the network. Also, we can fine-tune the architecture by changing the number of layers, the number of neurons, and so on. And deep models are great at using large amounts of data. In fact, the more data we have, generally, the better they perform. So this would be basically an important message in this course, is that deep neural networks help us solve these problems with machine learning, and instead of having to use lots of different models, we use the same basic idea of networks of neurons, and then we adjust the network to the problem that we're trying to solve, and the network will itself learn how to best represent the data to solve our problem. Okay, so to sum up this part, I gave you a brief overview of the course and this historical perspective on artificial intelligence and machine learning, and this basic idea that we need nonlinear transformations in order to solve more general classes of problems. So if we don't do this, we probably get stuck in just linear problems and cannot solve problems in general. And I gave you a promise about deep learning that it can help solve a lot of these shortcomings of classical machine learning. So for this, I would recommend chapter 1 of this book, Deep Learning Methods and Applications, and chapters 1 and 5 of Deep Learning by Goodfellow and others. So let's take a short break, and we're going to begin at 5 minutes to 5. So 16:55, I'll begin the next lecture. See you soon.